Good morning. I hope you guys can hear me. I'm Emmanuel. I'll be doing the last presentation from Group A on parametric amplifiers. Just to confirm if you people can hear me.
Yes, I can.
Okay, thank you. So I'll begin. So I'll be handling parametric amplifiers in this presentation. So I'll just start. So I'll start. What's a parametric amplifier? So these are type of negative resistance nonlinear amplifiers whose capacitive or inductive reactances are varied by local oscillators, and you'll come to see that the local oscillators are the pump signals, which usually operate at very high frequencies. For example, here we can have a parametric amplifier rated 4 gigahertz being operated by a 12 gigahertz oscillator. So this local oscillator will be trying to modulate the capacitive parameters of our circuit, the parametric amplifiers. So another signal, the input signal, which is also the signal frequency to be amplified, is also used to vary the reactance of this nonlinear component of the circuit. The capacitive negative reactance of the vector to the capacitive nature of this circuit, which we vary. So parametric amplifiers work by one principle, one main principle, which is transfer of energy from the high power pump signal to the low frequency signal, which is the signal of interest that we want to amplify its magnitude. So majorly you will find that we are magnifying very low level or low power signal that are of very high frequencies, and we want to amplify them with as little noise as possible. We want to amplify them with as little That's why we use parametric amplifiers instead of other the common amplifiers that we know, the transistor based and the vacuum tube amplifiers, which are prone to high noise that we want to avoid. Conventional amplifiers, the ones that I've mentioned, the transistor based and conductor, the transistors, transistor based and the vacuum tube amplifiers do not provide sufficient gain to detect low power signal above the noise floor. Yeah, so in this slide, you can see a parabolic dish here. It's called a Very Large Array Telescope, found in New Mexico in the United States. This parabolic dish is used to collect or to trap a high cosmic signal from the deep space, and we use the parametric amplifiers circuit so as to amplify those low level. You'll get to know that these cosmic signals that come from deep far in the space, they are sent at a very high frequency, but as they travel through the space, their amplitudes which is also their power, tends to decrease with the distance. So as they reach the Earth's surface and hit the parabolic dish, which are the receivers, they tend to have very low amplitudes, and that's where parametric amplifiers come to amplify those signals so that we can process them and collect information from them. So hidden within the parabolic dish at very large array telescope in Mexico is a circuit for capturing and amplifying very low level, ultra high and very high signals. Yeah. So an electronic parametric amplifier is used with very high frequencies, where the input frequency to be amplified may vary. So as I've told you, these are signals coming from deep in the space with very low power, but high frequencies. And there's need to amplify them so that we can get to process them. Yeah, so these circuits are also useful where conventional amplifiers do not provide sufficient gain to detect a signal above the noise floor. Yeah, so the main advantage of this parametric amplifier is that it can amplify very low level signals with as little noise as possible, compared to other conventional amplifiers, such as the transistor-based op-amps and also the vacuum tube amplifiers. So we'll move to how these parametric amplifiers work. So as I've told you, they work under the principle of transfer of energy from the pump signal to the frequency signals, to the signal frequencies, which are the signals of interest which we want to amplify. Yeah, so parametric amplifiers circuits provide adjustable amplification and up-down conversion of an input analog signal. This is done by applying second sinusoidal signal called the pump signal, which is a high power, high frequency signal, to a nonlinear reactive circuit element. The pump signal causes the reactance of nonlinear circuit element to vary sinusoidally at the same frequency as pump signal. So the core principle behind parametric amplifier is based on energy transfer from high power pump signal to low power input signal through nonlinear reactive components. So we are using the pump signal and the input signal to vary the parameters of the circuit, and the parameters of the parameter of this circuit is the capacitive reactance, which is a nonlinear reactive component of this circuit, and it's provided by the varictor diode. So the energy transfer occurs due to parametric variation of circuit properties. So here we are doing what we call the capacitive modulation of varictor diode, which can be adjusted by the pump frequency and the input signal. So after the circuits are set so that the pump and the signal are resonant, there's the change of energy, there's exchange of energy once we set the parameters of once we set the RLC legs. We'll see in the next slides. We will try to achieve resonance, and at resonance there will be that exchange of energy between the two signals, resulting in an amplified signal. So the components of our parametric amplifiers are the pump source, which produces the very high frequency, high power signal. Then we have the nonlinear reactive element. Here we have a varictor. We use the varictor whose capacitance is varied by the pump signal. Then we have the input, the signal input, which is amplified, which is the signal that we want to amplify. Then we have something called the idle frequency. So you'll come to see that the idle frequency is a is a is a is a is the difference is the difference frequency that comes after amplification to satisfy some conditions which we will see ahead. And then we have the output circuit which extracts the amplified signal. So those are the main components of parametric amplifiers. Yeah. So here I have a simplified, a very simplified parametric amplifier just to make us understand the basic operations of this amplifier. So in the circuit above, the varactor diode is the element C. So we say that we are making use of the varactor diode to use its capacitive component element to adjust the negative reactance to modulate its capacitive element. Yeah, so the varactor diode is represented by the capacitor C3. The RLC circuit legs on the pump and the input signal can be designed to be underdamped. So the pump and input signal will have some resonance. So we design the RLC components of the pump section and the input section to be underdamped so that we can achieve resonance. As I told you, we want to achieve resonance so that we have these two signals oscillating at a particular frequency, and at the moment when they are oscillating, then we have the exchange of power from the high power pump signal to our input signal. So yeah. So these allow capacitive modulation on the varactor diode to be changed by simply adjusting the input and the pump frequencies. Oh, sorry. So yeah, we have some types of parametric amplifiers. So these circuits can be configured as non-degenerate parametric amplifiers with separate idle frequency, and degenerate parametric amplifier where the idle frequency coincides with the input frequencies. So we'll go to the first one, which is called the non-degenerate parametric amplifiers. So they use three distinct frequencies: the pump frequency, the signal frequency, and the idle frequency. So the idle frequency is necessary for efficient energy transfer. Remember, I told you that out of the amplification of our input signal or the signal frequency, there arises an idle frequency to satisfy this relationship. So there's this relationship where the pump frequency should be equal to the sum of the signal frequency and the idle frequency. So we want to satisfy this condition whenever we amplify an input signal. So Fs will come out amplified, but there will be another frequency that arises to satisfy the condition called the idle frequency. And in that case, we have the non-degenerate parametric amplifiers. So the idler is usually an unutilized frequency, but its presence ensures better gain and efficiency. So these are commonly used in microwave and radar applications. Number two, we have the degenerate parametric amplifiers. So in degenerate parametric amplifiers, we only have two frequency components. We have the pump frequency and the signal frequency. The idle frequency, in this case, it coincides with the signal frequency. So they are actually equal. So these are typically used in quantum computing and ultra-low noise amplification. And then we have another set of parametric amplifiers called the OPS, the optical parametric amplifiers. These are mainly used now in the optical fields and used in laser and nonlinear optics. So in optics, we'll use the optical parametric amplifiers. So these are how they work. They work based on parametric down conversion, where high energy photon is split into two lower energy photons. So Davis and Amitai yesterday mentioned about the photon splitting uh, in their presentations, and I hope you guys captured that. So here we have the high energy. We have the high energy frequency omega p here in terms of radians, which you can see by the arrow. It has a higher power. It has a high power. It has a high power. And another input signal here is the omega s, the signal frequency or the input signal. So as I said, we want to amplify the input signal by energy transfer. So here you also remember the relationship that omega p must be equal to omega s plus omega I, or fp should be equal to fs plus fi. So you can see that our signal omega s, our input signal omega s, when it reaches this other end of the diagram, it's magnified. It's amplified. It's amplified. You can see two arrows, and its energy is increased. Its energy is increased. But to satisfy the condition, some other frequency called the idle frequency is also released from the process. So we have our input signal amplified by a certain gain, and then we have an idle frequency resulting from that process. So this is how the optical parametric amplifier works. So in optical parametric amplifier, the input is two light beam, omega p and omega s, where omega p is called the high beam. It's called the high beam frequency, and then this omega s is called the input uh, light frequency. So the OPA will make the pump beam omega p weaker and amplify the signal beam omega s, and also create a new so-called idler beam at the frequency omega I, where omega I is just the byproduct of that process to satisfy the condition that I told you earlier. So in OPA, the pump and idler photons usually travel collinearly through an nonlinear optical crystal. So phase matching is required for the process to work well, and also to have it stable. So we'll move to a parameter called the gain, the gain of these parametric amplifiers. So in determining the gain, because the gain here will determine how strong our signal, our output signal is, or our optical output is. So we have what we call the Manley-Rowe relation, which this relation just is used to get the maximum gain out of the parametric amplifiers. So there are a set of relations that are used to determine maximum gain of parametric amplifier using power conversion principles, conservation principles. So these relations are applied in the context of lossless, time-varying, and linear capacitance, where two sinusoidal signals of frequencies FP and FS are applied. By now, I know you understand what FP and FS are. So the output generates harmonics of these frequencies. The output generates harmonics of these frequencies, which are separated using narrow band pass filters and dissipated. Yeah, so this is a diagram just to illustrate the parametric amplifier. So the equations describes the power flow in an nonlinear capacitance system. When power is supplied by generator, the generator here is the pump signal and also the input signal. PM is positive. This is the power, the power into the capacitive element is positive, indicating power flows into the capacitance. So if the power output is positive, then we understand that the power is flowing into the capacitance from the pump signal, from the pump and from the input signal. So if power flows out, then the power is negative. So wherever you see a negative power out of the capacitor, of the capacitive elements, we know that the power was actually flowing out of the capacitor, and whenever it is positive, it indicates that the power flows into the capacitance. So we have in this we have what we call the sum frequency parametric amplifiers under this. Remember, we are under the gain. We are under the gain of parametric amplifiers. So we have what we call the sum frequency parametric amplifiers, also called the up converters. So when the output is at the sum frequency, when the output is at the sum frequency FP plus FS, the power gain GP is given by the equation below. So GP for an up converter will have the formula for the gain being Fs plus Fp over Fs. So here we'll have a positive gain above 1, which will amplify signal, which will amplify our signal upwards. So this device amplifies the signal by converting it into higher frequencies. Then we have the down converter. So as signal frequencies first and pump frequency FP produces lower output frequency. Remember, for the up it was producing a higher frequency, but in down converter we're producing a lower frequency by that equation. So this device converts the signal into a lower frequency. This results in power attenuation. So here this results in attenuation. You can see that the gain will definitely be below 1. So we will not be having it's basically attenuation. Yeah, it's basically attenuation, because Fs, you can see Fs is in the numerator, then we have Fp plus Fs in the denominator. So this type of parametric amplifier is called the down converter. Power gain becomes attenuation. So you'll come to see that parametric down converters are used are also called demodulators, because we are having the frequency signal output being lower, while the up converters are called modulators, because we are actually increasing the frequency higher and higher. So come to the merits of parametric amplifier. I told you the main advantage of parametric amplifier is the low noise advantage that it has. So it can able to since amplification does not rely on active elements, noise levels remain minimal. Yeah, so that's the main idea. You can see we don't have any transistors. We just have the RLC that we are taking use to ensure that we amplify the signals. So with minimal noise. So we have also another merit as high gain. So efficient energy transfer from pump allows significant signal amplification. So we can also tune because the inputs that are modulating the capacitance at the pump signal and the input signals. We can actually tune these frequencies to come up with the desired output. Yeah, so in that regard, they can be used in spectroscopy and also laser application. Then we have efficient power. They are power efficient energy transfer rather than dissipation, making parametric amplification energy efficient. Then high frequency operation really work with very high frequencies. You can see at microwaves, from radio range to microwave, and optical frequencies where conventional amplifiers really struggle to meet and achieve. We also have demerits. They say anything that has advantages must have disadvantages. And one demerit is a complex design, require precise tuning of pump signal and phase matching. So we want to achieve phase matching, and achieving this requires complex design of our parametric amplifier circuits. So the strong pump requirements it needs a powerful external pump source for effective operations. Then we have the bandwidth limitations. Traditional parametric amplifiers have narrow frequency range unless designed with broadband compensation. Then we have potential for signal loss. If not properly tuned, the signal may not amplify efficiently, leading to power attenuation instead of gain. Then we have instability issues. Uncontrolled pump fluctuation can lead to unwanted oscillations. So those are some of the disadvantages. Now on to the applications. As I told you earlier, you saw the parabolic dish for astronomical and cosmic observations and applications. They are definitely used in radio astronomy, used in deep space communication to amplify weak cosmic signals. Then we also have them applied in microwave and radar systems, where to enhance sensitivity for military and civilian radars. So this is to catch these very low level signals and get to process them. Then they are also used in quantum computing. You also understand that quantum computing works with very low level signals at very high frequencies. So we can't use the common amplifiers. We have to use parametric amplifiers if you want to take advantage and apply and try to process information at that level. Then we have optical communications. They're used to boost weak signals in long haul optical networks that joins continents in submarine cables. We can use optical parametric amplifiers to boost as repeaters. Instead of repeaters, we can use them to boost the signal as they travel, the optical signal as they travel. This is especially in long haul optical networks, and also low noise RF applications. Yeah, so that's our presentation. Thank you for listening. I can accept questions if there are any.
Yes, Emmanuel, Thank you. I have a few questions. There's the circuit diagram, and you mentioned the pump source and varactor diode. So I was wondering how, if you could maybe go to the circuit diagram and kindly help me understand how the pumping happens and why do we use, for example, a varactor diode and not any other type of diode in the construction of the parametric amplifier. And also there's the oscillator. If maybe you could, yes, explain.
Okay. Okay, so we are using the varactor diode because we want to make use of the advantage of its advantage of. We want to make use of its capacitive the capacitive voltage relation that the varactor holds. Remember, we are doing what we call we are using the inputs, the pump signal and the input signal to modulate the capacitive parameter of our circuit. And the capacitive parameters are provided by the varactor. So this varactor, we make use of its capacitive voltage relationship so as to modulate it, and it produces an amplified output with frequencies of harmonics of FP and FS. And then we have this LC2 and C2 as a band. What do we call them? A band pass to take the frequencies that are specifically required, the frequencies that are specifically required at the output. So we use the varactor to make use of the capacitive reactance. Remember, we are taking use of the capacitive reactance in the introduction. We say that these are type of non-negative reactance and linear amplifier whose capacitive inductive reactance are varied by local oscillator, which is FP, at several times the operating frequency of the amplifier. So we use the varactor to make use of its capacitive reactance nature. Yeah. And the other question was about oscillations. So I told you, let me just, yeah. So I said that we want our pump leg, our pump RLC leg, and our input RLC legs to be designed to be underdamped. To be designed to be underdamped so that we can achieve resonance. So after we have achieved resonance, then there is oscillation of these two frequencies, the FP and FS. They tend to resonate at resonance, and in the process of oscillating at resonance, we have the energy transfer between the high frequency signal FP and FS, releasing an output frequencies of FS amplified and the idle frequency. Yes. Don't know if I've answered you.
Yes, thank you.
Any other question?
For the idler frequency, does it have a specific value that you select, or any range works?
Not really, because for the idle, we'll just make use of the relation, because what we are interested in is this relation. You are interested in FS. You're interested in FS. So yeah, I think yes, because if you select FP, and you know FI, then you can get the desired FS that you want. So I think you need to choose so that you satisfy this relationship of frequencies.
Thank you.
Yeah, thank you so much.
Dr. Kwon, is there anything you'd like to add? Is there anything from you, Dr. Kwon?
Safin, I'm okay.
So do we wrap up today's class here?
Yeah. You can send in your attendance, no problem.
Okay.